Today, we want to discuss a little bit more about critical points. So fill in some things that we didn't fill in yesterday, but continue connecting this to the old stuff we did with optimization back in single variable calculus. Yesterday, I focused on the derivative solving f prime of x equals 0 to find the critical points. But remember, a critical point will happen when the derivative is equal to 0 or the derivative is undefined. We could get a few things happening here. When the derivative is equal to 0, that means the function is flat. The tangent is horizontal. So f prime equals 0 means we have a horizontal tangent because we have a local minimum. The horizontal tangent because we have a local maximum. Critical points themselves do not necessarily mean we'll have a local minimum or a local maximum. So it could be that the function just increases, flattens out, and then continues to increase. So we could have a local minimum. We could have a local maximum. Or we could have neither. So none of the above is a choice. So here are situations where f prime is equal to 0, because in these cases, we have a nice flat tangent line or a horizontal tangent line. But when we're looking for critical points, the point is that we're going to be looking for local maximums and local minimums. It could be that the derivative is just undefined. So for example, if we have an absolute value function, here we still have a local minimum. Or we could have an absolute value function going the other way and have a local maximum. But the derivative is undefined at these pointy parts of the function. We can't draw one tangent line, so f prime is undefined. We can't draw one tangent line. We could draw a horizontal tangent line, but that's not, there's an infinite number of tangent lines at each of these points. So we want to upgrade this to functions of two variables. So let's say A, B is a critical point of a function of two variables if both the derivatives are equal to 0 or if the derivatives are undefined. So yesterday, we just started with fx equals 0. Oops. So we just want to add to this. So notice that so this is what we started with yesterday. So that was our starting point from yesterday. Make sure the two derivatives are equal to 0. But we also want to capture this undefined business, because what if our functions might have some pointy bits in them that could be local minimums or local maximums. Add to the list of points that we have to check. So we want to summarize things a little bit. Here I want the two derivatives to be equal to 0. So we could summarize this by saying that AB is a critical point of f of x, y if the gradient of f is equal to the 0 vector. Because if the gradient is equal to the zero vector, that means fx is, if the gradient at AB is equal to zero, the zero vector, that means fx is equal to zero and fy is equal to zero at AB. So it's a way of capturing two derivatives equaling zero, because those two derivatives show up in the vector, the gradient. This also makes sense because the gradient indicates the direction of greatest increase, or the negative gradient is the direction of greatest decrease. And what this statement says is the direction of greatest increase is to not go anywhere. So that means you're at the highest or the lowest point. But just like before, we haven't seen an example that uses this, but the gradient can be zero, or just like we had with critical points before, if the gradient is undefined. So now we have a two-variable version of this critical point business. It involves the gradient, just to summarize, our two derivatives both being equal to zero at the point. That sentence came out weird, at least when I played it back just now. All right. Yesterday, we looked at an example that had a shifted center, but it was essentially this function. We know that this function had a global minimum at 0, 0. We have two x squared and y squared can both be at their lowest value 0. So the lowest value we're going to get from this function is 0, and that happens at the origin 0, 0. We can imagine the picture of what's going on here. We know that this is a circular paraboloid. We also know that the level curves are just concentric circles. Always draw the circles first. The level curves are concentric circles, 0 at the middle. And then as we move out, the circles get larger as they go higher up. We built the gradient of this function. Well, we took the two derivatives. So we had the parts to build the gradient of the function. And the only way to make this gradient is 0 is to have x and y be both 0. And we even looked at second partials. Two of the second partials were very telling. fxx at any point xy is 2. fxy at xy and fyx at xy were both equal to 0, and fyy at xy was equal to 2. This fits with what we know is going on in this on this surface. fxx is the positive 2. And if we look at just the x, if we look from the side, we know we get parabolas. So we know we have a parabola when y equals 0. Well, on the xz plane, we got this parabola when y equals 0. And if we look in the xz plane, the xz plane when y equals 0. If we look in the yz plane, when x equals 0, we also have a parabola going up. And our lowest point is at the bottom of the parabola from looking at it from one side, and the bottom of a parabola looking at it from the other side. So we want to see all this stuff happening in what we know the surface looks like. In the contour diagrams, here they are shrinking down to this lowest point. I should label my contours. Let's see, 1, 2, 3, 4. There's our contours. They shouldn't be evenly spaced. I should have gone with 1, 4, 9, 16. But then when we look at the side, when y is equal to 0, we are going to be looking at a parabola, z equals x squared. And this parabola is concave up, and that's what fxx is telling us. Fyy is telling us the same thing when we look at the other axis, when x is equal to 0, from the other axis, when x is equal to 0. So let's make one change, see how the values change, and then see how our intuition and how we visualize things changes. When you're doing math problems, it's less about the volume of the problems that you do, and sometimes it's more about the change between one problem to another. Let's take g of xy, and let's just make one of these terms negative. So our gradient of g is going to be 2x times I minus 2y times j. If we solve this where the gradient is equal to 0, that will happen at the origin, 0, 0. So if this equals 0, the 0 vector, that means that we have a critical point at 0, 0. If we look at our second derivatives, gxx at xy is going to be 2. Gxy at xy will be 0, as will gyx at xy. But gyy at xy will be negative 2. So here's fx is 2x, so gx is 2x, so gxx will be 2. Gy is negative 2y, so gyy will be negative 2. So the difference between our second partials gives us a different picture. When y is equal to 0, we go up to our function and think y is equal to 0, then we're looking at x squared, and gxx is equal to 2, we should see concave up. And that's what we do. That's what we see. When y is equal to 0, we just get x squared. So we have this parabola going up when y is equal to 0. But when x is equal to 0, we get a parabola facing the other direction. When x is equal to 0, we get minus y squared. So looking at these two kinds of concavity, I've got in one direction, I've got a minimum, and in one direction, I have a maximum. So let's take a look at, I don't have it going, there we go. Let's take a look at one of our favorite graphing calculators. And let's look at the function z equals x squared minus y squared. So when we look at what the surface looks like, we see that in one direction we have parabolas facing up, and in the other direction we have parabolas facing down. And so the geometry tells us that what we're looking at is a saddle point. So called because it like kind of looks like a saddle. Saddles aren't so pointy. They should be a lot flatter in the middle. If we look at our contours, we have these two lines that cross, and then we have all these hyperbolas. So what we end up with is a hyperbolic paraboloid. Any other cool information? There's our two derivatives, 2x, 2y. And then we ran out of time. So what we see is a parabola going up in one direction and a parabola going down in the other direction. Compare that to when we had a x squared plus y squared. We had a parabola going up in one direction . Oh, it doesn't give us a picture. There we go. Somehow I switched to a capital Z and that messed everything up. We see a parabola going in the x direction and going up in the x direction and a parabola going up in the y direction. And so that's why we get this, this paraboloid. And there we get our contours are circles rather than hyperbolas. So what we saw was a parabola going up in one direction and a parabola going down in the other direction. What we saw in the contours were hyperbolas, and these two lines, crossing at the origin, at the critical point, and then hyperbolas everywhere else. We're doing this before we get to the second derivative test, which just tells us how to put these four derivatives together and calculate what's going on, because we want to build some kind of intuition about what's going on when we look at a function. We can see where the critical point is going to be, and we can see the second derivative in one direction will tell us concave up, but the second derivative in the other direction will tell us concave down. So that's us building some intuition about what the second derivatives are going to tell us. Any questions? I didn't try to fill in the rest because I can't draw a hyperbolic paraboloid yet. I've been at it for 20 years and it still never comes out. Any questions? All right. So let's suppose that we have a point where the gradient is equal to 0, and then we can look at the second derivative test. For functions of two variables. So let's suppose that we have a point where the gradient is equal to 0. So specifically, the second derivative test is what we're going to use when the gradient is equal to 0. We're going to have to do some other stuff if the gradient is undefined at a point, because we won't be able to do second derivatives because first derivative is undefined. So let's just specifically look at the gradient at f at this critical point. We're going to calculate this. I think this book calls it capital D. Yeah. We're going to combine the four derivatives, second derivatives, into this calculation. fxx at AB times fyy at AB minus fxy at AB squared. So I'm multiplying the two second partial derivatives, fxx and fyy. And then we're subtracting fxy, the mixed partials, or the square of the mixed partial at AB. And then based on the value of D, we're going to make conclusions about what's going on at x naught, y naught. If D is positive and fxx is positive, so here are the things that can happen. If D is positive and fxx at AB is positive, then we have a local minimum at AB. Let's write down the next one that says, if D is positive and fxx at AB is negative, then then we have a local maximum at AB. Note that in both of these cases, if D is positive, we're saying local minimum or local maximum if D is positive in both of these cases. Also notice that we're only making our decision for local minimum and local maximum based on fxx for some reason. But at least this sign matches what we did before. If the second derivative is positive, then it's a local minimum because we have concave up. If the second derivative is negative, then we have a local maximum because the function is concave down. So interesting that D is positive in both of these cases, but now we're just looking at fxx. So why aren't we considering fyy? So that's the first thing that we should be thinking about. This should bother you. I'm just telling you why this should bother you. You should be looking at this and saying, wait, what about fyy? 4 derivatives, and you're telling me we only have to look at one? And this is why, because in both of these cases, the D is positive. Let's look at the third line. If D is negative, then we have a saddle point at AB. So for this saddle point conclusion, we only had to look at the value of D. If D was negative, then we have a saddle point. We didn't have to do, if D is positive, we had to look at the second derivative, fxx. But if D is negative, I don't care what else is going on. We just immediately jump to saddle point. We have left out a case here, but we should look at this and say, wait a second, if D is negative, then why don't we care about what's going on at the 2 derivatives, or the 2 second derivatives, 2 second partial derivatives? But there is one case that we've left out so far. I've got D is positive, D is negative. That leaves out D equals 0. If D is equal to 0, then we will have a local maximum, a local minimum, a saddle point, or none of these. That is to say, if D is equal to 0, we don't get to make a conclusion based on the second derivative test. The second derivative test is inconclusive. We have to do something else. So if D is equal to 0, the second derivative test is inconclusive. That is, do something else. You don't get to say inconclusive, because it's either going to be a local minimum, a local maximum, a saddle point, or none of these. You don't get to say inconclusive. You have to do something else to figure out what's going on at that critical point. You still have to figure it out. All right, let's take a look at this sign business. Let's start by looking at our at what's going on in this calculation of D. Fxx times Fyy minus the square of the mixed partials. Let's just for now ignore the square of the mixed partials term and look at how we're calculating D. So let's just pretend that we're not, let's just ignore that for a second. I have magnets in my notebook. And the pens are metal, so I have to block this out with a different pen. There we go. So let's pretend that we just have Fxx and Fyy, because this is where most of our information is going to come from. What's going on in the X direction? What's going on in the Y direction? What's the concavity in the X direction? What's the concavity in the Y direction? If D is positive, since we are subtracting, actually, I don't want to ignore this. If D is positive and we are subtracting something that is most definitely positive, because it's the square of Fxy, that means Fxx and Fyy must have the same sign. So down here, when we are concerned about not looking at Fyy, we're just looking at the sign of Fxx. And if D is positive, Fxx and Fyy must have the same sign, because they're either both positive or both negative. If D is positive, then Fxx and Fyy must have the same sign. So that's why we didn't worry about what's going on at Fyy. If Fxx is positive, then Fyy is positive as well. If Fxx is negative, then Fyy is also negative. So if D is positive, Fxx and Fyy must have the same sign. So that's why we only had to worry about one of them. D is positive, tells us that Fxx and Fyy have the same sign, so we'll have the same concavity in both directions. So I only have to worry about one of them because the other one is just going to match. But that also helps us when we get to the saddle point business. If D is negative, then we definitely have a saddle point because we got concave up in one direction, concave down in the other direction. If D is going to be negative, that means Fxx and Fyy have different signs. Or Fxy at AB is very large. So if D is positive, definitely Fxx and Fyy have the same sign. Most likely thing that happens when D is negative is that Fxx and Fyy have different signs. And just like with lots of things in math, if we make a calculation come up with 0, then lots of things can happen. We're going to have to, but the second derivative test is inconclusive. We're going to have to do something else. Remember, this is not like, this is kind of like in series when you're doing the ratio test. If the limit from the ratio test is equal to 1, the ratio test is inconclusive. You, in your analysis, do not get to be inconclusive. You have to come up with a conclusion, but you're not going to be able to use the ratio test to do it. You're still going to have to classify that critical point as a local maximum, a local minimum, or a saddle point, but you're not going to be able to use the second derivative test to do it. So the second derivative test fits with the problems that we've done so far today. In our saddle point example, where we are concave up when y is 0, but concave down when x is equal to 0, our calculation for d will be 2 times 2 minus 0 squared, which is negative. So our calculation for d in this problem with g is 2 times negative 2 minus 0 squared. D was negative, we have a saddle point. Intuitively, this makes sense because we have concave up in one way and concave down in the other direction. In our previous problem, fxx and fyy were both 2, so our calculation for d would be 2 times 2 is minus 0 squared, positive 4. And so since d is positive and gxx is positive, we have a local minimum, which happened to be also a global minimum. Any questions? Comments? So yesterday, we did not say how to combine all the 4 derivatives to make our conclusion, and so today that we did. Here's what the second derivative test looks like when you have a function of 2 variables. But also notice the similarities between what we're doing here and what we did in single variable calculus. In single variable calculus, we solve f prime of x equals 0, and then look at the sign of f double prime for the concavity. Here we're doing the same thing, solving f prime equals 0, and then looking at the sign of the second derivative. Any questions? Told you at the beginning of Calc 3 that Calc 3 is just Calc 1 and Calc 2 with functions of more than one variable. The thinking hasn't changed. Any questions? Comments? We all should feel a little bit silly that we spent so much time doing trigonometric substitution to integrate functions, and we should have spent more time thinking about things. But this is a traditional application of school. We're not here to think about things. We're here to do problems and be judged. Maybe we're missing the point at somewhere. I think we might be. But I'm not sure what the answer is moving forward. You know what I mean? No one asks me because we don't talk about things, but I brought up that I give you unlimited attempts to do the homework, unlimited number of attempts to do the quizzes. If I had something called a test, then you'd get unlimited attempts to do that, because I think that's the point. And then no one asks me, and no one asks anything after that. I think because the baseline assumption is at some point, I'm not going to give you a chance to fix your problems. I'm going to make you do some problems, and just whatever happened first, that's your score. You know what I mean? I think that's the baseline assumption. And I try to tell people, yo, I don't do that. If they're turning in problems to me and I'm going to grade them, if they get it wrong, I'm gonna ask them to do it again because I think that's what we're supposed to do. But then I think I'm supposed to be giving you just once, at least something with just one attempt to make sure that you can fail it. Because I don't think the school education system as it stands is designed to teach you things. It's designed to judge you. And if it's an American school system, make you feel bad for getting things wrong the first time. So that if you don't immediately succeed at something, you just like, oh, okay, never again. Maybe what we do is send the exact opposite message that we should be sending. You know what I mean? I guess my message is stop performing tests, especially stop doing tests for children. They're too young. They could probably handle the disappointment except for all the emotional baggage we as adults attach to it and make them feel bad, because children will look to adults for how they're supposed to feel about things. Kid falls over and scrapes his knee. If you laugh, then the kid will laugh too. If it's just like a scrape. Because they're trying to figure out what to do. If you freak out, then the kid will freak out too. You know what I mean? I realize that you won't believe me because I don't have human children. I have a dog. And if you're out walking your dog and you're like all mad, and you're like all, and you're just sitting there like muttering to yourself, your dog knows that you're mad, and your dog's going to get mad too. Your dog's going to go, yeah, what are we mad at? And then you're going to wonder why your dog is barking at other dogs. You told the dog to be angry by being angry, and the dog just wants to be like, all right, that's what we're doing today. It's like when your dog starts barking out the door, out the window at the mailman. If you start yelling at your dog, say, hey, stop that. The dog just thinks you're joining in on the barking. You're just reinforcing the barking because they're like, well, yeah, let's bark at that guy. So anyway, you know what I mean? All right, that's going to do it for today. We are, this second derivative test business on functions of two variables shows up in chapter 15, section 1, right at the beginning of optimization. The important part of chapter 15 is where we get to, is towards the end. But at the beginning, we need to make it look like the stuff that we've done before. My whole deal with Calc 3 is that it's just Calc 1 and Calc 2 with more variables running around. We're just modifying stuff that we had before to fit functions of two variables. All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.